Our universe is a strange and mysterious place. On the grandest scales, we have galaxies spiraling through the cosmos. But if we zoom in to the tiniest level, a whole new world opens up, the quantum realm. This is the domain of atoms and the particles within them, where the rules of classical physics break down. Quantum physics reveals a universe governed by uncertainty and probability, where particles can be in multiple places at once. This might sound like science fiction, but it's the very real science that underpins our understanding of the universe. It's a realm that challenges our intuition and forces us to rethink our understanding of reality. The development of quantum physics in the early 20th century was nothing short of a revolution in science. It overturned centuries-old assumptions about the nature of reality and ushered in a new era of scientific exploration. The pioneers of quantum physics, scientists like Albert Einstein, Niels Bohr, and Werner Heisenberg, grappled with these mind-bending concepts. Their work led to groundbreaking technologies like lasers, transistors, and magnetic resonance imaging, MRI. Technologies that have transformed our world and become an integral part of our daily lives. Quantum physics isn't just an abstract theory, it's the foundation of our modern technological world. It challenges us to embrace the strange and counterintuitive. While the realm of quantum physics might seem distant and esoteric, its effects are all around us. From the smartphones we use to the lasers that read our Blu-rays, quantum mechanics is woven into the fabric of our daily lives. Every time you turn on a computer or use a GPS device, you're benefiting from the principles of quantum physics. Without quantum physics, our digital world simply wouldn't exist. It's a testament to how quantum phenomena have been harnessed to create practical technologies that we now take for granted. In the quantum world, things don't always fit neatly into the categories we're used to. One of the most mind-boggling discoveries of quantum physics is that particles can behave like waves, and waves can behave like particles. This concept, known as wave-particle duality, is one of the cornerstones of quantum mechanics. Light, which we typically think of as a wave, can also behave like a stream of particles called photons. This is how solar panels work. Photons from sunlight knock electrons loose from atoms, generating electricity. This duality has profound implications for our understanding of the universe. If the idea of wave-particle duality has your head spinning, hold on tight because we're about to dive into something even stranger: quantum superposition. In the quantum world, particles don't have to be in one definite state at a time. They can exist in multiple states simultaneously. Imagine a spinning coin. Before it settles, it's a blur of both heads and tails. That's kind of what it's like for a particle in superposition. The evidence from countless experiments confirms that superposition is a fundamental feature of the quantum world. So, how do we describe these strange quantum objects that can be in multiple states at once? Enter the concept of quantum states. In classical physics, we can describe the state of an object, like a ball, by its position and momentum. But in the quantum world, things get a bit more abstract. A quantum state is like a set of instructions or a recipe that tells us the probabilities of finding a particle with certain properties when we measure it. Quantum states provide a framework for understanding and predicting the behavior of particles in the quantum realm. The transition from classical to quantum physics is like swapping a magnifying glass for a high-powered microscope. Suddenly, a whole new world opens up, full of intricate details and unexpected surprises. In classical physics, we assume that we can measure the properties of an object without disturbing it. But in the quantum world, the very act of observation can change the state of the system we're observing. This inherent uncertainty and the probabilistic nature of quantum mechanics might seem unsettling at first. But as we delve deeper into the quantum realm, we begin to appreciate the elegance and beauty of this strange and counterintuitive world. One of the most mind-boggling concepts to emerge from quantum physics is the Heisenberg uncertainty principle. This principle, formulated by Werner Heisenberg in 1927, states that there are fundamental limits to what we can know about a quantum object. The more precisely we try to pin down the position of the particle, the more uncertain its momentum becomes, and vice versa. In the quantum world, the act of measurement inevitably disturbs the system we're trying to observe, introducing an inherent uncertainty into our knowledge of its properties. This principle is a fundamental limit imposed by the very nature of reality. Now, you might be thinking, that's all very well for tiny particles, but what does it have to do with my everyday life? Surprisingly, the Heisenberg uncertainty principle has implications that extend far beyond the realm of atoms and subatomic particles. Consider the act of looking at a distant star through a telescope. The light from that star has traveled for millions or even billions of years to reach our eyes. But each photon of light carries a tiny bit of momentum. When that photon enters our eye, it interacts with the light-sensitive cells in our retina, transferring some of its momentum. This interaction, however minuscule, introduces a slight uncertainty into our knowledge of the star's position. The Heisenberg uncertainty principle has profound philosophical implications. For centuries, physicists believed in a deterministic universe, one where the present state of the universe completely determines its future. However, the inherent uncertainty of the quantum world throws a wrench into this deterministic view. Because we can never know both the position and momentum of a particle with perfect accuracy, the future of even a simple quantum system becomes inherently unpredictable. This doesn't mean that the universe is random or chaotic. Rather, it suggests that the universe is fundamentally probabilistic. The Heisenberg uncertainty principle doesn't limit our understanding of the universe, it expands it. It tells us that the universe is not a static, predictable machine, but a dynamic, ever-evolving tapestry of possibilities. It's a universe where the very act of observation can influence the outcome of events, where the future is not predetermined but full of potential. This inherent uncertainty might be unsettling to some, but it's also incredibly liberating. It means that the universe is not a closed book, but an open invitation to explore and marvel at the wonders that lie hidden beneath the surface of our everyday experience. Buckle up, because we're about to dive into one of the most mind-bending and awe-inspiring phenomena in the quantum world: entanglement. Imagine two particles, linked in such a way that they share the same fate, no matter how far apart they are. You measure the state of one particle, say its spin, and instantly you know the state of the other particle, even if it's light years away. This is quantum entanglement, a concept so bizarre that even Einstein famously called it spooky action at a distance. When two particles become entangled, their states become intertwined, like two threads woven together. They are no longer independent entities, but part of a single, unified system. Entanglement might sound like something out of science fiction, but physicists have been creating and studying entangled particles in the lab for decades. One way to create entangled particles is to start with a process that produces two particles in a definite quantum state. For example, certain crystals can split a single photon of light into two entangled photons. These entangled photons can then be separated, sent along different paths, and measured independently. What's remarkable is that the results of these measurements will always be correlated, even if the photons are miles apart. Scientists have entangled atoms, electrons, and even tiny vibrating diamonds. The strange and counterintuitive nature of quantum entanglement has sparked a flurry of research into its potential applications. One of the most exciting possibilities is quantum teleportation. Not the Star Trek kind of teleportation where objects vanish and reappear elsewhere, but the transfer of quantum information from one location to another, instantly, using entangled particles. Imagine wanting to send someone a secret message encoded in the state of a quantum particle. You could entangle this particle with another particle and send that second particle to your recipient. Then, by performing a specific measurement on your particle, you could instantly transfer its quantum state and the secret message it carries to the entangled particle at the other end. Beyond teleportation, entanglement is also being harnessed to develop powerful new computers, quantum computers. And that's not all. Entanglement holds the key to developing ultra-secure communication networks, where the very act of eavesdropping would disturb the entangled particles, alerting the intended recipients to the intrusion. Imagine a world where financial transactions, confidential data, and even national secrets could be transmitted with absolute security, impervious to hacking or interception. Quantum entanglement, once a theoretical curiosity, is rapidly transitioning from the realm of science fiction to the forefront of technological innovation. It has the potential to revolutionize communication, computing, and our understanding of the universe itself. As we delve deeper into the mysteries of entanglement, we unlock new possibilities, pushing the boundaries of what's possible and reshaping our understanding of reality. Imagine shining a beam of light at a wall with two narrow slits cut into it. You might expect to see two bright bands of light on the other side, corresponding to the light passing through each slit. This is what we observe in our everyday experience with waves, like water waves passing through a narrow opening. But in the quantum realm, things get a whole lot stranger. This seemingly simple setup, known as the double-slit experiment, has become one of the most iconic and perplexing experiments in the history of physics. It's a testament to the profound strangeness of the quantum world and our ongoing struggle to reconcile it with our everyday intuition. When we perform this experiment with particles like electrons or photons, something truly mind-boggling happens. Instead of two bright bands, we observe an interference pattern, a series of alternating bright and dark bands, as if the particles were interfering with themselves like waves. This pattern arises even when we fire the particles one at a time, suggesting that each particle somehow passes through both slits simultaneously and interferes with itself. This result is one of the most compelling demonstrations of wave-particle duality, the idea that quantum objects can exhibit both wave-like and particle-like behavior. When we try to confine the particle to a definite path by forcing it through one slit or the other, the interference pattern disappears, and we're left with the classical expectation of two bright bands. But when we allow the particle to explore all possible paths, as if it were a wave spreading out through both slits, the interference pattern reappears. It's as if the particle knows whether or not we're watching and adjusts its behavior accordingly. This seemingly paradoxical behavior highlights a crucial difference between classical and quantum physics. In classical physics, we assume that particles have definite trajectories, and that our measurements merely reveal those pre-existing paths. But in quantum physics, the act of measurement plays a much more active role. This brings us to one of the most hotly debated and often misunderstood aspects of the double-slit experiment, the role of the observer. Some interpretations of quantum mechanics suggest that it's the act of observation itself, the interaction between the measuring device and the quantum system, that causes the wave function to collapse from a superposition of states into a definite outcome. This has led to some rather outlandish claims that consciousness itself is somehow responsible for collapsing the wave function. However, most physicists agree that consciousness plays no special role in quantum mechanics. The observer effect is not about human consciousness. It's about the interaction between any measuring device and the quantum system being measured. This interaction inevitably disturbs the quantum system, introducing uncertainty and forcing it into a definite state. Think back to Heisenberg's uncertainty principle. When we try to measure the position of a particle, we inevitably introduce uncertainty into its momentum, and vice versa. While the Copenhagen interpretation, with its emphasis on wave-function collapse, remains the most widely accepted interpretation of quantum mechanics, it's not the only one. Other interpretations, like the many-worlds interpretation, offer a radically different perspective on the nature of reality and the role of the observer. According to the many-worlds interpretation, every quantum measurement, every interaction that could lead to multiple outcomes, doesn't result in a single outcome with other possibilities disappearing into the ether. Instead, each possibility branches off, creating a new universe, a new timeline where that outcome becomes reality. In this view, the double-slit experiment doesn't involve particles mysteriously choosing one path or another. Instead, the particle travels down both paths, but in different universes. Our consciousness doesn't collapse the wave function. It simply follows one particular branch of this ever-expanding multiverse. As we've journeyed through the bizarre and beautiful landscape of quantum physics, we've encountered mind-bending concepts that challenge our everyday intuition and force us to reconsider our place in the cosmos. We've seen how particles can behave like waves and waves like particles, how objects can exist in multiple states simultaneously, and how entangled particles can seemingly communicate faster than the speed of light. But for all that we've learned about the quantum realm, countless questions remain unanswered, tantalizing mysteries that beckon us further into the unknown. How do we reconcile the probabilistic nature of quantum mechanics with the seemingly deterministic world we experience every day? What is the nature of the wave function? And does it describe a real physical entity or merely our knowledge of a quantum system? And perhaps the most profound question of all, what is the true nature of reality? Does the universe split into countless parallel worlds every time a quantum measurement is made? Or is there some deeper principle yet to be discovered that governs the behavior of the quantum realm? These are not merely academic questions, for the answers have the potential to revolutionize our understanding of the universe and our place within it. They drive us to develop new theories, to devise ever more ingenious experiments, and to push the boundaries of human knowledge. The implications of quantum physics extend far beyond the laboratory, forcing us to grapple with profound philosophical questions about the nature of reality, the role of the observer, and the limits of human knowledge. Quantum mechanics challenges the deterministic worldview, suggesting that observation shapes reality. This has led to debates about consciousness in quantum mechanics and the nature of reality. These questions may remain unanswered, but they push us to explore the mystery and wonder of existence. While physicists continue to debate the philosophical implications of quantum mechanics, engineers and entrepreneurs are hard at work harnessing its strange and counterintuitive properties to develop groundbreaking technologies that promise to revolutionize our world. Quantum computers, with their ability to perform calculations far beyond the reach of classical computers, are already being developed to tackle some of the world's most challenging problems, from drug discovery to material science to artificial intelligence. Quantum cryptography, leveraging the principles of entanglement to create unbreakable encryption, promises to usher in a new era of secure communication, protecting sensitive data from even the most sophisticated hackers. And quantum sensors, exploiting the exquisite sensitivity of quantum systems to their environment, are being developed for a wide range of applications, from medical imaging to navigation to environmental monitoring. The quantum revolution, far from being a distant prospect, is well underway, driven by a virtuous cycle of scientific discovery, technological innovation, and entrepreneurial spirit. As we delve deeper into the mysteries of the quantum realm, we unlock new possibilities, pushing the boundaries of what's possible and shaping the future of our world. The journey into the quantum world is not for the faint of heart. It challenges our deepest intuitions and leaves us with more questions than answers. But it's also a journey of profound wonder, revealing a universe far stranger and more beautiful than we imagined. The universe is a dynamic, ever-evolving tapestry of possibilities. Observation can influence events, and the future is full of potential. As we embrace the quantum age, let us be curious and humble. The greatest discoveries are yet to come. In the words of Werner Heisenberg, what we observe is not nature itself, but nature exposed to our method of questioning. Let us continue to question and explore the wonders of the quantum world. In doing so, we deepen our understanding of ourselves and our place in the cosmos.